And all right. Anyone has any questions? Okay, we started with Okay, we started introducing something called the moments of inertia and related rolling motion to the rotational and translational motion. And one of the things about rolling motion is that if it rolls without slipping, there is a relationship between the rotational angular velocity to the translational velocity of the rolling object. Now, this is equal to r omega, and I'd like to write it the capital R because this is a specific R. Whereas any point on the rolling object, its tangential velocity v sub t equal to r omega. It looks the same, but the meaning is very different in that depends on the radius, how far that point is from the axis of rotation. So different points on the rotating object, different points along it will have different tangential velocity. Okay? So the tangential velocity at the outer edge of the rolling object, that tangential velocity, or the tangential speed, okay, that speed is the same as the translational speed of the rolling object. And that's what this is. The point of analyzing a rolling object in terms of its rotational motion and its translational motion allows us to write down the total kinetic energy of a rotating object, of a rolling object rather, in terms of the rotational kinetic energy, which is 1/2 I omega squared, and then you have the usual translational kinetic energy, right? This is the good old 1/2 mv squared. Now, the total kinetic energy then would be the sum of these two terms. And if you look at the expression for the rotational kinetic energy, 1/2 I omega squared, we saw that omega, the angular velocity, is rate of change, or how quickly the angle rotates through, right? It's very similar to the concept of translational velocity that measures how quickly you translate. So that is the analog, the rotational analog of velocity. And if you compare them, you see omega is analogous to the quantity v. And I then is the analog of mass. When you're talking about rotating object, it's not the total mass that is important, but how the mass is distributed. And it is all hidden in this so-called I, the moment of inertia. The moment of inertia would depend not only on the total mass, but also on how the mass is distributed relative to the axis of rotation. And we have formulas for various things. For example, if you have a hoop, a ring, so all the mass essentially is at a distance capital R if you want. I prefer to use capital R. Then the moment of inertia is just mr squared. If you have a disk that is solid and uniform, so all the mass is uniformly distributed, then you can show that the moment of inertia is 1/2 mr squared, okay? And so on and so forth. Now, we don't want to concentrate on those things. The moment of inertia is either given to you in the formula because it's a regular object, or it's given to you as a number that you can take to be experimentally determined, or someone did the calculation for you, or it is an unknown that cannot be calculated from formula because that's not necessary, but you use dynamics or energy conservation to calculate it. So as an example of energy conservation, we have this problem where you have a ring, so all of the mass is concentrated around the edge, right? And a solid disk, so the mass is distributed uniformly throughout the whole, if you want, the whole circle. It's actually a disk, so the whole disk. And when they start rolling down, and they roll because there's friction, otherwise you just slide down. So you have to understand the difference between sliding motion and rolling motion, okay? If it is rolling, then it has not only translational kinetic energy, but rotational kinetic energy. You add those two terms together. And together with the fact that V is equal to R omega, these are related, you can add the two of them together and you find that the total kinetic energy is given by this. So this is the translational term. If you multiply it out, V over R is omega. So you get 1/2 I omega squared. That's the rotational kinetic energy. And in a case like this, when it is just rolling down, there's no sliding, there's no work done by friction, and you will have what is called conservation of mechanical energy. And conservation of mechanical energy tells you that the total potential energy at the beginning, U sub I, plus the total kinetic energy at the initial stage, which is at the top here, this must be equal to U final plus K final. And if you take the bottom of the ramp to be the zero of potential energy, then your initial potential energy is mg times by h. H is the height of the ramp. All right, that's how far above the zero level your objects are. So that will be the potential energy of the ring or of the disk. Now, because they start out at zero speed, they are not rotating, they are not rolling, they are not moving, not translating, the total kinetic energy will be zero. And when you reach the bottom of the ramp, your total potential energy is zero. And that leaves you with total final kinetic energy, which is this term. It's a sum of the translational part and the rotational part. And one thing you can understand is if you lose potential energy and part of it goes into the rotational part, then you end up going slower than if you just slid down. If you just slide down because it is smooth, you would reach the bottom first, okay? Because all of the potential energy that you lost goes into translational kinetic energy, and therefore it has a higher total energy. Just look at this. If you allow rotation, this term is larger than 1. And because of that, you divide both sides by this quantity, you divide by something larger than 1, you end up with something less than 1. So compared to when it's not rotating, it's just sliding, then this term is 0 and you have 1. Your 1/2 mv squared is just mgh. Or if you want, v squared is 2gh. But if you have something else that's smaller, then it's now smaller than 2gh. So it's got a smaller velocity. Now we can apply that to the disk and the ring exactly, because we can work out what I is. Now, as I wrote down here, for the ring, I is mr squared. So if you look at the term, now I know this is little r here, it really should be big R, okay? But doesn't matter. If you use I as mr squared over there, then I over mr squared would be 2. Sorry, 1. So 1 plus 1, you have 2 there. Okay? Now, if you use the disk, I is 1/2 mr squared. So 1/2 divided by itself, you get 1 plus 1/2. So it's a different factor. Okay? So you will find that because the moments of inertia are different, the larger the moments of inertia, the larger your rotational kinetic energy will be. And therefore, the ring, having a larger moment of inertia, will have a larger fraction of its energy in rotational form. Therefore, the translational kinetic energy is less, and you would know from this argument that the velocity at the bottom, the translational velocity at the bottom, is less for the ring than for the disk. And if you actually have a race, if you go to YouTube, you can probably find it. It's too difficult for me to bring it here. We have this contraption that's this big, and you actually can roll a disc, a sphere, and a hoop or a ring, and you can see that the one with the smallest moments of inertia would arrive at the bottom first. Okay, now we can do the calculation if you want, but I think it's the subject of the next problem, so it will clear everything. Now look at the figure. If you go bowling, it says after you pick up a spare, your bowling ball rolls without slipping back toward the ball rack with a linear speed of 2.85 meters per second. So that's in the drawing at this point, right? It is moving at 2.85 meters per second. I hope you can see it. And when it moves along, it comes up to this ramp, and then it's going to rise up. Okay, rolls up a ramp that rises a vertical distance of 0.53 meters. So that's also indicated in the drawing. All right, so the question is, part A, what is the linear speed of the ball when it reaches the top of the ramp? Now, this is an object that is rolling, and if it's rolling, friction doesn't do any work, and mechanical energy will be conserved. So you use conservation of mechanical energy to solve the problem, okay? And that means, once again, you write down U initial plus K initial is U final plus K final. Okay, that's what conservation of mechanical energy means. Now, initially, you are down at the bottom of the ramp. And if you call that the zero of potential energy, in other words, you call that level y equal to 0, then mgy would be 0. Therefore, you have 0, that's the initial kinetic and initial potential energy, and then you have your kinetic energy. Now, initially, your kinetic energy is 1/2 mv initial squared, all right, and you have the translational plus the rotational part. Now, as the ball rolls along, it doesn't change its shape, so its I doesn't change, its M doesn't change, its R doesn't change. This is actually a constant, this factor. Now, this is the initial kinetic energy. You have to equate this to the final, this is the initial mechanical energy. You've got to equate that to the final mechanical energy. when you rise up 0.53 meters, your final potential energy is mgh. Now I'm going to leave that as h. And you also have kinetic energy once you are on top of the ramp. And it has exactly the same expression, except that you are talking about the final position, so it's v final squared. But this is the same one. Oh no. Oh, this is going to be painful. All right, I think what I can do is do this. No. Well, it's just going to take up all the time there. Oh. Anyway, you can just go do it, right? You have 1/2 mv final squared 1 plus I over mr squared. Okay. Now, yes.
Could you just write that part on the board after?
Okay. Now, the reason I bring this up is because I know that many people, they want to run to the calculator and start punching in numbers because they want to write down the mass and the velocity that they know, the things that they know, and it's fine and good. You can calculate, I think what they want to know is what is the speed, right, at the top. Once you climb up to the top of the ramp, what is the speed? So they want to calculate V final. You know the mass, you know the height, you know the initial 2.85 meters per second squared. And for a bowling ball, you find that for a bowling ball, I is 2/5 mr squared. Okay? We're assuming that it is a solid ball as opposed to a shell that's hollow inside. Okay, it's not hollow inside, it's solid, and you can look it up. They'll tell you it's 2/5 mr squared. So essentially, if you put this in, this factor becomes 2/5 mr squared over mr squared. You will get 2/5, and that is the same for both sides of the equation. So you end up with 1/2 mv initial squared. 1 plus 2/5 is 7/5. Okay. Now this is where you can do algebra. You can just divide both sides by m, and then you multiply everything by, this is 1/2 7/5 is 7/10. So if you multiply everything by 10/7, you get V initial squared is 10 over 7 GH plus V final squared. So far, all I make use of is that it is a solid ball that's rolling. I have not made use of anything else. And from here, I know H, I know V initial, I can calculate what the initial, what the final speed is. Now, as I was saying, the reason I brought this up is because if you look at the question, part B asks, if the radius of the ball were increased, how would the speed change? The only way you can answer that question is not to put any numbers in.
Professor,
Yeah.
question.
Yeah. It's 1 plus 2/5 mr squared divided by mr squared. Okay, you just substitute for I in here, you get 2/5. Then 1 plus 2/5 is 7/5. Okay? Yeah. The reason I put it in this form and not put any numbers in is because in order to answer part B, you cannot substitute all the known quantities in, because at the end you don't know how it depends on R. But if you put everything in terms of just symbols, then it's very clear in the end it doesn't depend on R. And therefore the answer to the question that is asked, if the radius of the ball will increase, how would this speed change? The answer is it doesn't change. You can use a little ball bearing or a big, huge bowling ball. You roll it up the same ramp, they have the same speed at the bottom, they will have the same speed at the top. Doesn't matter what the radius is. Okay? What does matter is whether it's a solid sphere or a rolling pin. I once told the Physics Society of Physics students to challenge the Math Society students to a bowling contest. I said, then when you show up with a bowling, show up a bowling pin that is the width of the garters. So every time you bowl, you always will get a strike. I don't know. People just don't get my jokes. Anyway, so this is just something that you can go ahead and do, right? Now, let's do something that I did not cover from chapter 9, but this is very important in trying to understand motion of extended bodies. This is what you would have to invoke if you try to understand any macroscopic object that you would encounter. So, for example, if I want to throw a football, okay, it's not a point. It is a ball that has dimensions, got extension. All right. How does it behave? I don't want to talk about boomerang because they have a lot of external force acting on the boomerang, which causes it to come back. But most other objects, when you throw, it is a big object, and you have to understand how spin would affect its motion, for example. Or if I take a ruler and I throw it, it doesn't just do this, right? A ruler doesn't just move like that when I throw it. Catch. Okay? When I throw it, you can see that it tumbles along, right? It's not a pure trans. I've got to see the doctor right away after class because I've got a problem in my eye. But anyway. So we are trying to understand motion of extended body. I'm trying to find an excuse for not catching the pen. But I do have a problem with my eye. I mean, I can barely keep my right eye open. But anyway, so we have to understand something that's called center of mass. It's crucial, and I would bring in there are a lot of very interesting things. It's difficult to understand, but I like to show them to you so that you get an appreciation of, how the shape of the body affects the motion. And today we'll learn something about how they actually move for an extended body. So you understand how this thing, at least one point of it, how it will move. So this is the concept of center of mass. Now, many people are used to center of things. Perhaps you know about center of attention. I hope in this class, when you come here, I'm the center of attention. When you go to a party, I'll be a wallflower. But That's a different thing. When you watch a football game, where is the center of attention? Where the football is, right? You always follow the ball. People can get clobbered on the sideline, you won't see it, you just see the ball. Anyway, what I want to talk about is something called center of mass. Now, I think a lot of you understand the concept of center of population, right? If you go to, for example, the state of Alaska, where do you think the center of the population is? What's that?
Near Anchorage.
It's probably near Anchorage because most of the people in Alaska live in that city, right? Only the nuts live out in the wilderness. So the majority of the people be there, that's the center of population. So we have the same thing. By that you understand that that's where the majority of the people is. So center of population, population refers to people. When I talk about center of mass, what am I referring to? What quantity am I referring to? Mass. So if I talk about center of mass, where do you think it ought to be? Suppose I gave you this. This is a collection of objects, right? And I ask you, where is the center of mass of this collection of objects? Where would you put it? Let me give you a few choices. Okay, is it here, 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 or here? A, B, C, D, or E? A. All right. If you can't see that as A, I should speak to you privately. But you say that's the center of mass because most of the mass is around this point, right? It's near that point. Okay. But you actually make an implicit assumption there. That is that all those objects are the same. What if I told you these are all cotton balls, but that one is a solid piece of gold? Where is the center of mass in this case? Where would it be? If
Gold's heavier.
I hope you know that gold is heavier. Yeah, I mean, it is. It's actually not heavier. It's more like denser. We'll talk about that maybe at the end. So where do you suppose the center of mass is? It will be here. It will be close to the goal because that's where most of the mass is. So when you actually talk about center of mass, you have to weigh more heavily objects that have greater mass. This is what we call a weighted sum. And we are going to define center of mass mathematically as this quantity. All right. So we'll start off easy. We'll talk about one dimension. If you line them up, you've got two objects, M1 and M2. They are on the x-axis. This is the origin, O. And M1 is at the point x1 and M2 is at the point x2. And I now ask you, where is the center of mass? Now you know that it has to be closer to the heavier object. All right, the more massive object. And how would you define it? We're going to define it as a weighted sum. So the coordinate is important, but it has to be weighted by how much mass is there. That's why it's a product of the mass times by the coordinate. Okay? It's a weighted sum, so this is the weighting and this is the sum. You just sum up the mass times by coordinate of object 1, add to that object 2, and you divide by the total mass. All right, this will be called the center of mass of the two. So clearly, if let's say M1 is 0, this has no mass. Where is all the mass? It's here. You put that into the formula. If M1 is 0, you will get M2 M1 is 0. M2, x2 over M2, you get x2, right? That's where you want the center of mass to be if all the mass were there. If they are equally weighted, if M1 equals M2, where is the center of mass? It should be in the center, right? Because they are equal. And if you put M1 equals M2, you can take it out, you get x1 plus x2 times by m, divided by m plus m divided by 2m, you get x1 plus x2 over 2. x1 plus x2 over 2 is the average of those two numbers, which would be in the center. Okay? So it has all the characteristics that you want for what you would, in your gut, feel to be the center of mass. Now, so it's just a statement that the center of mass is closer to the more massive object. Now, this is in one dimension, and we don't live in a one-dimensional world. You can ask, what if I have many objects and they're all over, I strew them all over this room? Where is the center of mass? And it turns out that all you do is you calculate this thing. It's a similar thing, right? It's a weighted sum. You weight it, you weight the coordinate. How important is that coordinate? It depends on how much mass is at that coordinate. And you can talk about the x coordinate and the y coordinate. In fact, you can have an exact same expression for the z coordinate in this world. This one would be, I strewn, toys are all strewn all over the floor of this room. Where's the center of mass of those toys? Then you can talk about an x and y coordinate system, right? It would be depending on where the objects are, it would be some point on the floor. And how you find the x and y coordinate, that's how you calculate it. Now, we are not going to get you to calculate these things, although there are some problems that deal with it. What I really want is for you to get a good feeling for where the center of mass of an extended object is, because that's an important point. All right. Now, if you look at your physics textbook, it's roughly made of this uniform material, right? Paper all over. The ink is not that important, the weight. But whatever the case is, the center of mass is near the geometric center of the book. I hope you know what the geometric center is. If you take this room to be a box, and that means it's uniformly filled with the same material. Where is the center of mass? It'll be at the geometric center of this box. Where is the geometric center? I hope everyone can see it somewhere here, in space somewhere out there. Between the ceiling and the floor, equidistant from that side, equidistant from this side. Okay, that's where the center of, the geometric center of the room is. And if you fill this up uniformly, it will coincide with the center of mass. Of course, we know that if I fill it up differently, if this is made of very massive objects, massive material, then the center of mass will shift towards it. But most of the time, we deal with uniform material. So for a sphere, the center of mass will be the geometric center. If you actually look at this as a bowling ball and you have 3 holes here like that, right? Can you see the 3 holes there? Where would the center of mass be? Strictly speaking. I hope everyone can see that it is moved this way, away from the center and away from the 3 holes. Because the 3 holes is an absence of mass. You have to weigh this part more than that. They actually have a problem in the book with a 3/4 size pizza, and they tell you where the center of mass is and ask you for different things. But the thing I want you to note is, and I don't understand why they would use this. I mean, it sank. You can't find it anymore. But I always talk about a donut. Where's the center of mass of the donut? It's actually at the geometric center. the thing that's important to note is the center of mass doesn't have to be inside the body. In fact, I can shift my center of mass by changing my body shape. Okay? It's not a fixed point. Right now, my center of mass is inside my body. If I shift it like that, my center of mass is actually in space. It's not a point inside my body anymore. Okay. Now, what is the use of the center of mass? Why do we talk about it? Well, you will see the importance of the center of mass when we look at the collection of objects and allow them to move. Okay. Now, it can be a rigid body, like a pen that I threw, or like a baseball bat, or a soccer ball, whatever. Or it could actually be a loose collection of objects. So it's actually very, very general. Now, I want to do it quickly because it's difficult. It's not really necessary for you to be able to do this, to conceptually understand enough to solve problems. But I want to do it fairly quickly just to show you that this is not something that is that difficult. And for those of you who want to get at the details of it and want to understand things better, you can go back and try to reproduce it yourself. But if you look at the x center of mass position, we wrote that as m1 x1 plus m2 x2 over the total mass, which I'll write as capital M. It's m1 plus m2. It's the total mass of all the objects in my system. If my system is the baseball bat, that's just the mass of the baseball bat. Okay? Now, this is the position of the center of mass. Now, if you allow the objects to move, right, M1 would move, M2 would move, M3 would move, and they can move whichever way they want. My point is, if they move, then I can talk about what it is at an initial time, what it is at a final time, right? So I can talk about x center of mass final. What would that be? This would be m1 x1 final plus m2 x2 final. It's just at some final point. And obviously you have the same thing for another point, which I call the initial point. All right. If you want, you can think of a baseball bat like that. This is the initial point. So if you look at this as M1, that would be the X1 position. If this is M2, that would be the X2 position relative to some origin. And after it has moved, it will move to some place like that. This is the final. Different points, okay, if this is 1 may have moved here. 1 would have moved to a different X position, right? But I don't care. I have an initial, I have a final. I can just calculate where the initial center of mass X position is. Now, I do this because now I can talk about, hey, the center of mass has changed. Over here, the center of mass may have been, let's say, roughly around here, and now it has moved to this point, right? It has moved. So I am now interested in how long did it take to move there? In other words, what is the average velocity of the motion of the center of mass? How would I calculate the average velocity? I would just say final minus initial divided by the time taken, right? This would be the velocity of the center of mass, x component. And if you look at this, I would just take this this subtract this. So I just have m1 delta x1 plus m2 delta x2 over total mass. And I divide by time, I divide by delta t. What do I end up with? Delta x1 divided by delta t. That's the rate of change of the x component. That will be the x component of the velocity. And if I let the time interval shrink to 0, I'm talking about the instantaneous velocity. So the instantaneous velocity of the center of mass is equal to, lo and behold, this expression. m1 v1 plus m2 v2 plus as many of them as there are divided by the total mass. Okay? So this follows from this. If you just go back and crank, it's just from what you understand velocity to be, and you just turn the crank. You just sit down and do the algebra, and you will get this. And in a very similar way, you can say this position, the velocity of the center of mass can also change. How would it change? What is the rate of change? What's the instantaneous rate of change? That's what I call the acceleration of the center of mass. And it works out to be m1 a1 plus m2 a2 and so on and so forth divided by the total mass. Now the reason I want to get to this stage, this is the important thing. It seems that all I do is I need to know what m1 times by the acceleration of the first particle, the first object. What is this equal to? What is ma equal to? What's that? The net force on object 1. I may have 100 million objects, they're all moving around. What governs the motion of object 1 is the net force on object 1. What governs the motion of object 2 is the net force on object 2. So all I'm going to do now is to look at the net force. I don't care whether it's 1 or 2 or 3 or 1,345 particle. Whatever that object is, the mass times by the acceleration of that object is the net force on that object. So remember, I have to add up all these terms, right? m1 a1 plus m2 a2. I keep adding them up. So in other words, I have to add up the net force on object 1 plus the net force on object 2 plus the net force on object 3 and so on and so forth. Now, if you recall, when we talk about conservation of linear momentum, we distinguish between internal forces and external forces. And the idea there was that because of Newton's third law, if you have object 3 and object 13, and they interact with each other, that is, they exert forces on each other, those forces always cancel. So when you look at the net force on object 3, there is a term that is like that. The net force on object 13, there is an opposite force. So when you add the net force on 3 and the net force on 13, those net forces go away. The bottom line is this. If you look at this, you sum over all of the m1, a1, m2, a2, and whatnot, you end up only with external forces, sum of external forces acting on the system. That's why when you talk about like a baseball bat that you're throwing, the baseball bat retains its shape because the atoms inside the baseball bat, they are attracting one another to keep the shape constant. But every atom is also subject to an external force. What external force is that? You have a baseball bat here. What external force is acting on the baseball bat? Gravity is always there. And what this tells you is If I add up all the forces on all the atoms, the only thing that matters is the net gravitational force acting on the object. Okay, now let me write down the expression and you'll see it. We arrive at the acceleration of the center of mass is m1a1 plus m2a2 over the total mass. And the sum of this term is just equal to net external force divided by the total mass. So it's very interesting. You have an object, I don't care what its shape is. If you have a lot of external forces acting, I have an object, I tie a string there, I pull on it. I tie a spring here, I pull on it. There's gravitational force pulling on it. There can be a lot of external forces pulling on it. And if you look at this, you find that the total mass times by the acceleration of the center of mass is just the net external force. Okay? So this is the so-called Newton's law for a system of particles. It is that the total mass times by the acceleration of the center of mass is equal to the net external force. So this tells you something very interesting. It says that you have a collection of objects, and I don't care how they push and shove on each other, the center of mass of the system behaves like a single point object, as if all the mass will concentrate at that point, and all these external forces are acting on that point. Because that's what you started learning when we introduced Newton's laws, right? We introduce Newton's law, we always say, okay, draw the free body diagram like a point. And then put all the external forces, all the forces acting on that object. And then you apply Newton's laws and you talk about how it moves. Now you start worrying, what if I have an object that looks like a bat? It's this long. I'm pulling on it at this end, I'm pushing on it at this point. How does it move? I mean, it's a very complicated motion, right? If you imagine a bat and you pull on it that way and pull on it this way, it's not going to move this way, it's not going to move that way, it's going to have a complicated motion. It's rotating, it is accelerating. But what we have just shown is that I don't care how complicated the shape is, I don't care what forces you have acting on this object. You can treat that like a point, or at least there's a special point that moves such that all the mass is exerted at that, concentrated at that point, and all the external forces are acting on that point. So at least you can know something about the motion of the center of mass. As a consequence of it, so that's what I wrote down here. The center of mass accelerates just as though it were a point, and all the objects, all the external forces are acting on that point. Now you will celebrate the 4th of July very differently, because this is an example of the center of mass motion. You know that when you have all these fireworks, right? They shoot something up into the air, right? And then it explodes. And then you see all these pretty colors, all these pretty patterns. But what if you can note is that when it is projected, when it is shot out before it explodes, it is one body, a tight ball of gunpowder and all kinds of chemicals and whatnot. And it is launched upwards. And if you ignore air resistance, you know how it moves, right? We already learned. If you ignore air resistance and you throw something up, you project something up, it's going to follow a parabolic path. It's a trajectory of an object under free fall, right? It's going to move this way. And what you find is that even if it explodes, when it explodes, not all these different parts go all over, right? But it remains true that the center of mass of the exploded part would follow the parabola. I don't know if your book has it. I can take a hammer and throw it and show you in slow motion. You identify where the center of mass of the hammer is, and when you throw it, the hammer is going to be doing this. All right? It's going to be spinning about its center of mass. But if you just follow the center of mass, it follows a perfect parabola. You can see that. Now, many of you here know about perhaps the Russian airline was went down because of a bomb. If it were really true, once it lost power, the bomb can explode the parts into the plane into thousands of pieces. It doesn't change the fact that those are internal forces. The only external forces acting on all those parts, whether the plane is intact as one body or exploded into 100,000 pieces, is still gravity. If you ignore air resistance, it would still be following a parabola. And in fact, this is how, if you locate some large pieces, you can figure out where the other large pieces are, because you would know it will follow a certain trajectory. So if it follows this way and it explodes this way, if you find a large piece there, you're going to find another large piece here and not somewhere else, because it has to, the center of mass has to follow the laws of physics. Okay, so you can talk about fireworks. This is the picture that denotes this, right? When it explodes, it starts doing this, but it is moving, and it becomes bigger, and then it becomes bigger. But if you look at the center of mass of this, or the center of mass of this, or the center of mass of this, they follow a parabolic path. All right, so that's the use of the center of mass. Now, so far, it seems very abstract. How do we figure out the center of mass? Oh, you've got to do that calculation. Actually, there's a very practical way of finding the center of mass. See, if you take an object like this, and I want to balance it, how would I balance it? Say, oh, trial and error, I can balance it. And it turns out that where the point of balance is, that's where the center of mass of the object is. Okay. One way you can see that, and we'll talk about torque. It's amazing, I won't get to it. And you'll understand it in a different way. But one way you can understand this is if the center of mass is the point where all the mass is concentrated, well, this is larger, this is larger than that. Center of mass is closer to the larger object, the more massive object. This is where all the mass appears to be concentrated. So if I put my finger there, like this, if all the mass were concentrated there, it would just sit there, right? Because if the mass were concentrated to one side or the other, it would just fall. So the balance point actually is where the center of mass is. If you want to find the center of mass of this piece of paper, it's very simple. You take a pin and you pin it. You see how it's free to rotate somewhat? You will find that eventually the center of mass, you will understand this when we talk about torque. The center of mass is along the line straight down, because that's where the mass is concentrated. So it will be there, because if the mass, if you imagine a pendulum bob, right? If it's sitting right there, it wouldn't move. But if you bring the pendulum bob to one side and you release it, it will move. So if it is true that all the mass will concentrate at this point, it would stop, it will hang freely, when the center of mass is on this line. So to find the center of mass, all you do is you pin it, you let it hang freely, you draw a straight line down through the axis, through your pin. Then you go to another point and you pin it. You draw the straight line down. Where they intersect is where the center of mass is. Say, wait a minute, what if I take a third path? Would they all intersect at the same point? And the answer is yes. You can go back and try to pin it any number of points and you draw the straight line down. All the straight lines would all intersect at one point. And that's where the center of mass of the object is. Let me get started with this. Chapter 11. We're going to talk about rotation, and we're going to talk about extended bodies, which is why we talk about center of mass and whatnot, right? So we'll come back to center of mass soon. The first thing is, if I want to rotate an object, so now you can look at the world a little differently. When I'm trying to open the door, I'm not really trying to open the door, I'm trying to rotate an object. Okay? People don't find it amusing. Anyway. From experience, if I ask you, that's a heavy door, push it open, what would you do? You have to push, right? You have to apply a force. But you know instinctively from your experience, where would you push? If I ask you, where would you push? Yeah.
Far away from the axis of rotation also.
If you look at the door, where is the axis of rotation? The hinges. The door swings about the hinge, right? So that's what we call axis of rotation. This is where the hinges are, and it rotates about this line. This vertical line. This is an axis of rotation. Okay? And you know that, you all know this. You know, even if you're a little kid in kindergarten, you know this. We just need to quantify what you know. That is, you push as far away from the axis of rotation as possible, as far away from the hinges as possible. Now, what else? As the door opens, what do you find yourself doing when you're pushing? What is the direction of your push?
Forward, angle.
Can someone see that? Okay, let me put it to you this way. Right? If I'm going to push the door, as it rotates, what do I maintain? Look what happens to my finger. Can you see that it is rotating with the door? What I try to do is to keep what? Keep the force tangential to the rotational motion, to the circle. Okay, because that's when it is most effective. So to quantify these things, it turns out that if you're interested in rotation, so this is like the top view of a revolving door, right? You push this way. You don't push close to the center because you have to apply a much larger force. It's more effective if you're farther away. All right. If you have a nut and you have a wrench, you know that when you use a wrench, you're going to push at the far end of the handle and not here. If you're a plumber and you have a very tough nut to loosen, what do you do? What do plumbers do? Do you know about, sometimes they take a pipe and stick it in here so that the handle becomes longer, they can push. And it's all because they want to get as far away from the axis of rotation as possible. So all of that tells you that the effectiveness with which an object would rotate, is dependent not only on the magnitude of the force, but also on the point of application of the force. You want to keep it as far away from the axis of rotation as possible. So we define this quantity called torque. Torque is the product of the force, the tangential force. You see, when I try to push this, I know to push this way. I'm not going to push that way. I'm not going to push that way. I'm not going to push that way. I'll be foolish to push this way, right? I know to push in the tangential direction. So the torque is defined to be the tangential force multiplied by the radius of rotation. Okay? So it is R times F. It will have units of newtons times meters. Okay. Now we also know that when we want to make it very effective, and if you played the merry-go-round before, you would know that if I want to get this thing rotating, I'm never going to pull, right? If you apply a force this way, this would never rotate. From experience, you know that you actually want to push or pull tangent to the radius of rotation, right? So what happens if you actually apply a force that is not tangent to the circular arc around the axis? This is where knowing that force is a vector becomes useful. Because if this is a vector, I can always replace this by two forces. Because this plus that equals that. That's how you add vectors. But we know that if this single force is to be replaced by these two forces, and the one that is along the radius, this one along the radius, this force doesn't do any rotation. So you might as well only apply this force, the so-called tangential component. All right? The radial component of the force does not contribute to any rotational motion. So if you're interested in the rotational part, you want to calculate the tangential component of the force multiplied by the radius of rotation. Okay? So the more general definition is the following. And this is where we make it more abstract. In fact, I wouldn't draw a circle. I would just draw a potato. Because it can be any shape. And I will stick an axis of rotation through the potato, and then I say, okay, I apply a force. Now, in this case, I draw a circle because this way, this is constrained to rotate this way in the circle. And we just got done saying that what we really want is the tangential component of the force. We don't want the radial component. So if the angle between R, so think of it this way, you have axis of rotation, you have a point of application of the force, right? This is where you apply the force. This is where you pinch on it and pull. This is where you tie a rope and pull. Whatever the case may be. This is where you fasten a rocket and it wants to move that way. In other words, you're applying a force in this direction at this point. I call it the point of application of the force. Now, you've got this vector from the axis to the point of application, and you have the force vector. Those two vectors have an angle between them. Any two vectors have an angle between them. The tangential component, if you look at it, is always a sign of the angle between the two vectors. That's generally true. whenever you have two vectors, the tangential component, the component that is along one of the vectors, is always going to be sine of that angle. Okay? So you can write the torque as R times by the tangential component of the force. But if you look at the geometry, if this is theta, that's alternate angle, that's also theta. If this is R, then sine theta, if you form this triangle, this is R sine theta. So I can bring this sine theta term and group it with R, and then write that as R perpendicular times by F. This quantity, R sine theta, which is this quantity, is called a moment arm. Now it's easier than that. Just think of this, right? Axis of rotation. This is your force. What is the perpendicular distance between a point and a line? What would you take that distance to be? I hope everyone can see that. That's what I mean by the moment arm. A point and a line, there's only one unique distance. You can do this for another drawing, right? Axis of rotation, line of force. Can you see this is the perpendicular distance? That's the moment arm. You can do many of this. So one way, there are many ways to calculate the torque. One is just R times F times sine of theta. All you need to know is the radius vector, which is the vector from the axis to the point of application of the force. And the other one is the force vector. The angle between them is theta. That's always RF sine theta. The other way to do it is to remember, you've got a line, you've got a perpendicular distance. The torque is the force times by the perpendicular distance. Yeah, sometimes one way is easier than the other. Okay? So we will make use of that to figure out things next time.